What they found in the deepest place on the Sun isn't a location at all. It's a distance. On Christmas Eve 2024, a spacecraft called Parker Solar Probe flew closer into the Sun's atmosphere than anything humanity has ever built, and what it found there breaks a rule that has puzzled physicists for generations. The Sun's visible surface sits at around 10,000 degrees Fahrenheit. Its outer atmosphere, the corona, stretching millions of miles above that surface, somehow runs past 3 million degrees. Step near any fire on Earth and feel it for yourself. Walk away, and the heat fades within a few steps. How does a region farther from the flame end up hotter than the flame itself? Above the Sun, walking away only makes it worse, and nobody has ever fully explained why. The person who first predicted why the Sun even behaves this violently was a physicist named Eugene Parker. In the 1950s, standing in front of a blackboard, he proposed that the Sun wasn't just glowing quietly in space. It was constantly releasing a stream of charged particles in every direction, what he called the solar wind. Most of the scientific community rejected the idea outright. A star that never stopped exhaling material into the solar system sounded absurd. Then spacecraft data confirmed it. So did something astronomers had already been quietly recording for years. Comet tails that consistently pointed away from the Sun, no matter which direction the comet itself was traveling. It was faint photographic evidence of exactly the kind of outward pressure Parker had described. Parker had been right, and decades later, NASA formally named this mission after him. His discovery only deepened the mystery. If the Sun is constantly releasing that wind, something has to accelerate it. Something has to heat it. And whatever that something is, it seems to be adding energy to the corona rather than losing it. To find out, engineers at Johns Hopkins Applied Physics Laboratory built one of the strangest machines ever launched. Not a spacecraft designed to avoid heat, one designed to survive inside it. In a clean room, technicians in full protective suits fitted a carbon composite heat shield, nearly 5 inches thick, onto the spacecraft's sun-facing side. That shield alone would absorb temperatures approaching 2,500 degrees Fahrenheit, hot enough to soften steel, while the instruments tucked directly behind it stayed close to room temperature. Picture standing on either side of it during closest approach. On the sunward face, heat intense enough to vaporize most materials on Earth within seconds. On the other, quiet. Instruments humming along as if nothing extraordinary were happening at all. By late 2024, after repeated gravity assists around Venus to shed speed and bend its path, Parker reached the closest approach ever attempted. Each flyby used Venus's gravity to pull the spacecraft's orbit tighter around the Sun. It was a years-long process of trading distance for speed, one pass at a time. The final trajectory brought it within roughly 3.8 million miles of the Sun's surface. It was moving at nearly 430,000 miles per hour, fast enough to cross from New York to Los Angeles in under 30 seconds. Then the signal stopped. No telemetry, no live updates, nothing. For 2 full days, Mission Control had no way to know if the spacecraft had survived its own trajectory. There was no way to send a correction if something had gone wrong. There was no way to do anything but wait. When the data finally came back, scientists realized the Sun was behaving in ways they couldn't fully explain. Magnetic fields folded sharply backward on themselves. Streams of charged material appeared to reverse direction mid-flight. Regions that should have cooled the farther Parker traveled instead grew violently hotter. Researchers now call these magnetic folds switchbacks. Picture a river suddenly bending backward against its own current before snapping forward again, and you have a rough sense of what Parker measured moving through the solar wind. Had they finally found the one clean answer to the entire heating mystery? For a while it looked that way. Magnetic fields can store enormous energy. And if those folded structures suddenly collapse or reconnect, that energy could pour directly into the surrounding plasma, heating the corona from within. But the deeper researchers dug into the measurements, the less complete that explanation became. Switchbacks accounted for part of the heating, not all of it. Meanwhile, ESA's solar orbiter has been watching the same star from farther out since 2020. It uses its own suite of cameras and particle detectors to observe structure, while Parker moves directly through the material itself, close enough to be shaped by the very forces it's trying to measure. One mission sees the shape from a distance, the other feels it from inside. Together, the two spacecraft are building a picture of a star that behaves less like a stable burning sphere, and more like a constantly shifting magnetic system. None of this stays near the sun. The solar wind that Parker is now flying through eventually reaches Earth. Under normal conditions, our planet's own magnetic field deflects most of it, curving the charged particles harmlessly around us before they ever touch the ground. But when a solar storm arrives violently enough, that shield gets overwhelmed, and the consequences are immediate. Solar storms can interfere with satellites, disrupt GPS, damage communication infrastructure, and in extreme cases, overload entire power grids stretching across continents. In 1859, a solar storm known as the Carrington event generated electrical surges strong enough to set telegraph lines on fire in the middle of the night. It also lit up the sky with auroras as far south as the Caribbean. A storm of that scale today would strike a civilization that depends on satellites and electrical infrastructure every second of every day, which means whatever is happening at the deepest place Parker has ever reached doesn't stay there. It reaches here. Humanity has now flown a machine into the atmosphere of a star. Not metaphorically, physically. And instead of settling the question of how the sun works, the closest approach in history only exposed how incomplete that understanding still is. Magnetic waves rising through the corona. Continuous micro-reconnection events firing across the solar atmosphere. Turbulence transferring energy between plasma and magnetic structures in ways nobody has fully mapped. Each explanation accounts for part of the picture. None of them close it completely. Somewhere inside that brightness, in the deepest place any spacecraft has ever gone, the part of the sun that should be cooling down is still getting hotter, and no model built so far can fully account for it.